Okay, here I'm not really going to be doing any integrations. I just want to show you what you need to do when some integral questions appear the way these ones appear. So if you see the integral of the square root of a squared plus x squared, all right, so you see the sum of these two perfect squares appearing under the square root sign. So what do you really do? Well, in this situation, what we really need is to get a single term, a single perfect square under the square root sign, all right, so that when we have the perfect square, a single term under the square root sign, the square root and that square can go away. We leave us with just a function that we can handle easily, all right? So the first thing, what you really need to do in this first case is you want to make a trigonometric substitution. And we say x should be a tangent of theta. If we call x a tan theta, all right, this will be the square of that. That will be a squared tangent squared of theta. And we can take out the x squared from the square root. And the next thing we notice is that we are going to be having some trigonometric identity that we can identify. For example, tangent squared of an angle plus 1 will give us secant squared of that same angle. That will become a single term on the square root can take care of the square, which leaves us with just secant, which we can easily handle. That is the beauty about that. So when you see the sum of two perfect squares under a square root, or even if it's not under a square root, for example, this case, let's see. In this case, you have, for example, if we have the square, the integral of, let's say, 1 over a squared plus x squared over the x variable, all right? In this case, we can still make use of the tangent. The reason is we can't resolve this partial fraction because this does not have real factors, all right? Okay, so this, in this case, we can still say let x be this, all right? Now, over here, if we have this, what we really have to substitute is we say let x be, well, this is a minus x squared. When you see a number, a perfect square, or even if it's not a perfect square, you can make it a perfect square, all right, by taking the square root and then taking the square. A squared minus x squared, all right? In this case, we really need to start off by saying let x be sine theta, all right? When we make this substitution, it will give us a single term in here, because if you take the square of sine and then subtract it from 1, we're going to have cosine squared, right? After factorizing the a square out of the square root sign. Okay, and lastly, this one, if you have the square root of x squared minus a, so it's like the negative of what we have inside here, all right? We make use of the secant substitution. We say let x be a secant theta as the first thing. Then the next thing is just to try and cancel some things and then try and see how you can find the antiderivative. So these are the three basic things you need to take note of, including this one. Now let me add something for you so you don't be confused, all right? If you are given 1 over, let's say, x squared minus a squared over the x variable to integrate, take note, this is different from this, and it is also different from this. If you are given the square root of x squared minus a squared. In this case, the sign substitution will also work. Sorry, the secant substitution will also work here. But over here, you use partial fractions, right? Because you can easily resolve this with partial fractions. But over here, you will need the secant because of the square root. We need a single perfect square to take care of that square root. All right, this wasn't really, I wasn't going to solve anything. We're just going to show you the forms, because some functions will be coming up with, we'll be having this kind of forms, right? And you need to know how to deal with them. All right, thanks for watching.